Hello, everyone. Welcome back to ILTA Physics Online Lecture. Today, we're going to talk about accelerated motion in one-dimensional motion. Motion where the velocity of an object changes. The change in velocity during motion is called acceleration. So first, we'll define acceleration mathematically, and then we'll describe accelerated motion using motion diagrams, which we already learned about. This new concept of acceleration is a very important physical quantity that explains many different kinds of motion, and it will be applied in many areas later on. As always, let's do a quick review of what we learned last time. Well, quick might be difficult here. In the previous lecture, we studied uniform motion, motion where the velocity of an object stays the same. Let's quickly summarize again. In terms of displacement, uniform motion means the object moves the same distance during equal time intervals. In terms of velocity, it means the motion has the same magnitude and the same direction at all times. That perfectly explains uniform motion by the definition. And here's the method we'll use again today. A motion diagram perfectly describes uniform motion with equally spaced dots and arrows showing its direction. I told you a picture is worth 1,000 words. Now, let's look at the position graph. A position graph shaped like a straight line with a constant slope represents uniform motion. Why? Because the slope of the position graph is velocity, and since a straight line has a constant slope, the velocity is constant. That's uniform motion. Wait a second. Can you all tell me how the slope on a position-time graph becomes the velocity? Well, think about the definition of velocity, displacement over a time interval. On the graph, that's exactly what the slope shows. Once you understand this clearly, you don't need to memorize it. Understanding comes first. Here's one more important point. So far, we've said that the position graph of uniform motion is a straight line with a constant slope. That's describing uniform motion using the position graph. But now we should also be able to think in the reverse direction. In other words, when you see a straight line on a position graph, you should immediately recognize, oh, this is uniform motion. On the test, they might show us a position graph like this and ask what kind of motion it represents. Since we are already talking about position graphs, let's consider this. If the position graph is a straight line sloping downward, what kind of motion does that represent? Exactly, it's uniform motion to the left at constant speed. A negative slope means negative velocity, which means motion to the left. Until you get used to this, pay extra attention. Now let's look at the velocity graph. For uniform motion, the velocity graph is simple. Since the motion has a constant speed, the graph shows a constant value in the graph. Here's an important fact of the velocity graph. The area between the velocity and the x-axis, that shaded region in the figure below, represents the displacement of the object. In terms of equations, this relationship looks simple and obvious. This physical fact will also apply to accelerated motion, which we'll study today. It gives us a very useful way to calculate moving things quantitatively. So just remember for now, the area under the velocity graph equals the object's displacement. We'll explain it more later. Finally, if we express uniform motion in terms of kinematic variables, here's what we get. The speed is constant, and the final position of the moving object is the initial position plus the displacement. We can calculate it like this. These kinematic formulas will definitely appear on exams, so make sure you both understand the meaning and also memorize the equations. Wow, that review took quite a while, but reviewing like this is very important. It helps you understand and remember. The fact that the review took a long time means we learned a lot last time. What's more important is that we understand what we learned and can explain the relationships. Now, let's move on to today's new topic, accelerated motion. Let's add in acceleration. So, what is accelerated motion? When an object moves, it naturally has velocity. If that velocity doesn't stay the same, if it changes over time, then that motion is called accelerated motion. And in this case, acceleration is defined as the change in velocity over time. We can write that as an equation like this. Remember, a change in velocity can mean a change in magnitude, a change in direction, or both. Now, are you getting more comfortable with writing this definition as a formula? As you can see, acceleration is the change in velocity divided by the time interval. Notice how this is very similar to how we define velocity in uniform motion. The unit of acceleration, according to the definition, is meters per second squared. And just like velocity, acceleration is a vector quantity. It has both magnitude and direction. Later, when we look at the graphs, we'll see that the slope of the velocity graph is acceleration. Here is a short preview. Acceleration is closely related to a new physical quantity we'll learn in the next chapter: force. Newton's second law, the famous formula F equal ma, expresses the relationship between force and acceleration. That shows just how important acceleration is. We'll keep using this concept again and again. Now, let's pause and think about one last thing here. We said both velocity and acceleration are vector quantities. But in the formulas on this page, they're written like scalars without vector notation. Why is that? Remember from last time, when an object's motion changes directions a lot, velocity and speed are different. But if we divide the motion into shorter intervals where the direction doesn't change, then velocity and speed can be treated as the same. That's the idea we'll use from now on. So in formulas, we'll use the simpler scalar form. But in your head, you should always keep the distinction in mind. Simple math, but full motion needs to be in your mind. Now let's think a bit more about acceleration. We defined it as the change in velocity over time. Since velocity is a vector, the change includes both magnitude and direction. But here, we'll make things simpler with two assumptions. First, the direction of velocity doesn't change, only the magnitude does. Second, the acceleration is constant. In other words, the motion we're dealing with here isn't all that dynamic. This simpler type of accelerated motion is called constant acceleration motion. An example is shown in the diagram on the left. Think of a car slowly increasing its speed. The magnitude of velocity is changing, but the direction stays the same. That's constant acceleration motion. On the other hand, there are motions where the magnitude stays the same, but the direction changes. Circular motion, like in the diagram on the right, is a good example. The green velocity vector has the same length, but its direction keeps changing. We'll study circular motion in detail in the next chapter. So, is it reasonable to focus on constant acceleration motion as our assumption? Yes, because as we said earlier, if a motion involves direction changes, we can divide it into shorter intervals where the direction doesn't change and analyze those separately. In other words, we solve a complex problem by breaking it into several easier ones. This method will be very useful in many areas later on. So far, we've defined acceleration and looked at its properties. Now, let's use it to describe motion. Let's start with motion diagrams. Accelerated motion means velocity is changing, and we call the change in velocity across time acceleration. So, how exactly does acceleration change velocity? Since we are focusing on changes in magnitude only, acceleration either speeds up or slows down the velocity. This depends on the directions or signs of velocity and acceleration. You can see the directions in the figure and the signs in the equation. Remember, they mean the exact same thing. If they're in the same direction, the object speeds up. If they're in opposite directions, the object slows down. Think of it like this. If I'm running forward and the wind is pushing me from behind, I'll definitely speed up. But if I'm running forward and a strong headwind blows against me, I'll slow down. Just keep the directions of my velocity and the wind in mind, and you'll quickly see when I get faster or slower. Using motion diagrams, here's how it looks. For uniform motion, the diagram shows equally spaced dots with arrows pointing to the right, since the velocity doesn't change. The lengths of all arrows are the same, which means the acceleration is zero. In the second diagram below, where the motion speeds up, acceleration is added in the same direction as the motion. And again, we'll only consider cases where the acceleration is constant in each interval. In the example below, the object starts moving, speeds up, then slows down to a stop. The green arrows in the motion diagram show this clearly. Now look carefully at the accelerations in each interval. When speed increases, acceleration is in the same direction as velocity. When speed decreases, acceleration is in the opposite direction. Think back to the running example and remember the wind's direction. So how do we show opposite direction acceleration in equations? Since both velocity and acceleration are vectors, we show direction using plus or minus signs. I'll just keep going over it until you are comfortable with it. One last thing to mention clearly. When I gave the running examples with wind blowing behind me or against me, the wind itself is not the acceleration. It is the cause of acceleration. In other words, it is forces. And in the next chapter, we'll study in detail how forces affect velocity and acceleration. That's the end of today's lecture. Next time, we'll actually calculate accelerated motion using kinematic formulas. It feels like our learning is also picking up acceleration. Let's keep moving forward step by step, making sure we understand everything clearly. Great work today. Thank you.